much like we're doing cross sections that are circles. Okay, so if it's in terms of x, you're going to have, now notice I put the pi outside. You don't have to put the pi outside. The pi could also go inside, right? Because it's just a coefficient. So coefficients, we can put them on the inside, or we can pull them out on the outside of the integral. So essentially, we're just integrating pi r squared. And I used a capital R right here, and we'll see as we go to the next sections why I want to use a capital R for that. Today, there will be no lowercase r's and no holes in things, so we won't have to worry about that. But this is like our equation for our radius. So it's a little like our S, really. We could still kind of call it our S if we wanted to here. And then the only thing that changes is if it's a vertical axis is that you're doing everything in terms of y. So you're looking at the y-axis for your limits. You're looking at having a dy there. So let's just do a problem. Okay, we've got to find the volume of the solid formed by revolving the region bounded by the graph of f of x equals sine x and the x-axis from 0 to pi about the x-axis. So first of all, we're thinking about what our region is. So let me get my highlighter so I can highlight this part here. It is just the region bounded by the graph of sine of x and the x-axis from 0 to pi. So we're looking at this region right here. Now what's a little bit different about these problems, so on the ones we were doing before, we were building cross sections on that base, right? Here we're rotating this line around, right? So every little piece gets rotated all the way around. What's the shape going to kind of look like when we do this? Can you picture it? It's a little bit like a football shape, right? Here. So what's going to happen is that if we think about how we did like our S before, I'm not going to call it S now because we're rotating. If we do a little vertical strip right here, and then we take this point and we rotate it all the way around, then that is going to be our radius. Right? So I am going to call that capital R of x. There's a reason I'm calling it capital R, because we are going to eventually do this where we have like sort of a inside radius and an outside radius, because we're going to have a hole going through the middle of whatever we've got, right? But right now there's no hole, so I'm just going to use capital R of x. Little r of x is coming tomorrow, so stick with the capital R. Normally I wouldn't care as much, but I do care on this one. So capital R of x works a lot like that S, right? You want to look at the top of that line for that little line, and you're going to use the function that lies on that line. So there, that is on the graph of square root of sine x. So we got square root of sine x, and then we're going to subtract whatever we get at the bottom. Now today, that's pretty much always going to be 0. We're going to see some coming up where it's not 0. But for today, it's pretty much 0. So our capital R of x in this case is just the square root of sine x. And so we want to integrate our area formula when you're rotating is pi r squared, right? So I kind of like to leave the pi out front, but be careful, it's really easy to lose it. If you want to put it on the inside there, it's fine. Pi times the radius squared. But our radius is going to be our capital R of x. I don't know why that highlighted that. And we're going to square it, right? So when I plug in, so what I just wrote is just like the formula you use every time. I am going to plug in the square root of sine x squared. Right there, right? So we're just plugging in our capital R of x. what limits should I use on this integral? For dx, so I need 0 over 2 pi. So 0, 2 pi. Now, before I integrate, I'm going to simplify this even a little bit further. What is the square root of sine of x squared? Just sine x. What do you get when you integrate sine x? Negative cosine. So negative cosine x. Don't lose the pi. It's really easy to lose that pi that's out front. And we're going to evaluate this from 0 to pi. And then we will have pi times negative cosine of pi minus negative cosine of 0. Be really careful on this one about not just plugging in 0 for that second part, because we're going to see it's not going to be 0. So if I'm thinking of unit circle, cosine of pi, that's over here. That's negative 1, 0. So cosine's x coordinate. So I'm getting negative 1. This is really going to become like a plus. What is cosine of 0? 1. Here. This double negative becomes a positive, and I get 2 pi. This is a good example of one they might give you without a calculator, because that was pretty straightforward on your integration there. Okay, so it's similar to our cross sections, except for you're always using pi squared. If you see something being revolved or rotated around the axis, pi squared is your formula that you're using. There. Let's look at another one. Okay, this one we're going to have to graph. We're supposed to find the volume of the solid formed by revolving the region bounded by f of x equals x to the third plus 1, y equals 0, and x equals 2 around the x-axis. So let's graph this. I like to do my horizontal and vertical lines first. So y equals 0, what is that? X-axis. So that is the x-axis here. And then x equals 2. So x equals 2 is a vertical line here. And then let's do this in green. I would just make myself a little table here to make sure I got the points exactly right. So if I plug in 0 cubed plus 1 will give me 1, so I've got 0, 1. If I plug in 1, I would get 2. Oh, I think we'll have a problem here, aren't we? On my graph. Is your graph like this? It's the same graph. I've made a bad graph here, because what do I get when I plug in 2? 9, which does not fit on my graph. So I need to go all the way up here. And we'll just stick it up here. There. I really need some more points, because I've got this here, but that doesn't connect to my x-axis, right? What other number should I plug in? Let's try negative 1. Negative 1 to the third is negative 1 plus 1 will give us a 0. So that will help us out here. So we are looking at this region here. And we are going to rotate this around the x-axis. So we are taking, when you're rotating around the x-axis, you are taking like a vertical strip right here, and you're rotating that around the axis. So there's your radius. So for that radius, you're going to get that top of that line hits x to the third plus 1. The bottom of the line just hits 0, and that's going to be the case most of the time here. In fact, well, until we start rotating around other lines, like around x equals 2 or y equals 3, that's going to be the case. But right, I guess I should still put it though. Let's put minus 0. We need to be in the habit of doing that, because when we start rotating around like x equals 2, this is going to change. So the bottom of that line intersects right there at 0. So my capital R of x is x to the third plus 1. And so we need to integrate pi times that radius squared, right? So I'm going to do pi integral radius x cubed plus 1 squared dx. What should my limits be? -1 to 2. We're looking from the x-axis there for this. Let's treat this one like a non-calculator FRQ. So we can use we have to integrate by hand, but we don't have to simplify. Let's treat this one that way. So what do I need to do before I can integrate this? I got to expand it because I don't know how to integrate with that extra square right there. So this would be equal to the pi times the integral of x to the 6th plus 2x cubed plus 1. There. And then you would need to integrate from here. So when I integrate this one, Lucas, what will I get? The pi will kind of hang out front. What will I get when I integrate x to the 6 plus 2x to the third plus 1? Increase that exponent by 1. Divide out front by that new exponent, so that's going to be 1/7 right here. What would I get for the next one, Lucas? Let's do it together. So I have x to what power? 4th. And then I've got to do 2 divided by 4 out front, right? Which we can reduce to 1/2 here in a minute if we want. And then what about that last one where I've got the plus 1? That is just x, because it's like it's got an x to 0 here. There's not any 0, so you increase that exponent by 1. There. Like that, so it's -1 to 2. And then if this is a calculator or if this is a free response question, what we can do, we got to keep the pi out front. We're going to have 1/7 times 2 to the 7th plus, I'm going to make that 1/2 times 2 to the 4th plus 2 minus 1/7 times -1 to the 7th plus 1/2 times -1 to the 4th plus -1. There. We're going to treat it like it's FRQ, so there would be no sense in us trying to simplify all that, because there's a decent chance we'd make a mistake. Okay, questions there? All right, let's continue. Let's do one where we rotate around the y-axis. Okay, so we got the volume of the solid formed by revolving the region bounded by the graph of y equals x squared, or 2x squared, x equals 0, y equals 8 in the first quadrant around the y-axis. So I always like to graph my vertical and horizontal lines first. It kind of gives me a frame of where I'm looking at. So x equals 0, which axis is that? It's the y-axis here. Y equals 8. That's a horizontal line at 8. We do. I don't think I'm going to do it to graph it, because it does not matter as far as graphing goes. So I'm going to graph it like it is right now. But because this is in terms of y, we're going to have to solve that for the y here in a minute. But since we're so used to just plugging in x's and y's, I would just go ahead and graph it from here, because it's going to be the same graph even if we solve it, if we switch it. So if I plug in 0, I get 0. If I plug in 1, I get 2. And if I plug in 2, I'm going to get 8. And so this is a quadratic that looks like this. And bounded by these 3 lines, we've got this area right here. Okay, like Connor was asking, this is in terms of y, so y equals 2x squared is not going to be helpful to us. Let's go ahead. If I've got y equals 2x squared, I could divide both sides by 2. I get y over 2 equals x squared. And then I could square root both sides. Technically, when you square root both sides, you're getting plus or minus the square root of y over 2. Now, you have to pick one here. You can't do any problem with the plus or minus in it. Which part of the graph am I looking at? Are my x coordinates going to be positive, or are my x coordinates going to be negative over in this section? Positive, right? So we are going to go with x equals positive square root of y over 2. That's this section of that quadratic right here. So that's x equals square root of y over 2. No, limits will be y for this, because we need to solve for x so that the values we're plugging into our formula are going to be y. So our radius here, since we're rotating around the y-axis this time, we are going to do a little horizontal strip right here. And we're going to take that and rotate it around that x-axis, and this will be, I'm sorry, y-axis, and that'll be our capital R. So capital R of y here, thank you. Was that fine? Okay, thank you. I appreciate it. That's okay. I was going to send somebody down if I... Thank you. Okay, so capital R of y is going to be, we want to do right minus left on this one. So, so right side is on the equation square root of y over 2. And then left is on the y-axis, which is 0. Today, that second number is always 0. Tomorrow, it's not always 0. So, be on the lookout for that. Is it tomorrow or I can't remember what order I do this in. Later this week, for sure. It's not always 0. So our radius is just square root of y over 2. So now that we've got our radius, we're ready to set it up into pi r squared, right? We integrate pi r squared. And so we will have pi integral of the radius, which is the square root of y over 2 squared. And we'll do dy. And as we were saying, Aiden asked about those limits. They need to come from the y-axis. What would they be, Aiden? 0 up to 8, right there. So we're looking over here on the y-axis, not 0 to 2. Okay, this one becomes easier because what happens whenever we square the square root? They cancel each other out. So this is just going to be pi integral from 0 to 8 of y over 2 dy. I would think of it like this, integral from 0 to 8 of 1/2 y dy. So really, that 1/2 could even be pulled out front, right? So that would be 1/2 pi, or pi over 2, integral from 0 to 8 of just y dy. Yeah, if you leave it in, that's fine. It doesn't hurt anything. It's just you're going to deal with it one way or the other. There. And so at this point, I'm going to actually integrate the 1/2 pi, or let's just make that pi over 2. That stays out front. When I integrate y, has the exponent of 1 right now. Increase my exponent by 1, that gives me 2. Divide out front, that gives me 1/2. And so 0 to 8. Okay, and then I've got pi over 2, 1/2 times 8 squared minus 1/2 times 0 squared. And this one we'll simplify. 8 squared, 64. Half of 64 is 32. This is just 0. So I've got pi over 2 times 32, which I can put over 1. That gives me 32 pi over 2. 32 over 2 is 16. So I get 16. Okay. Questions? Everything we're going to do today is going to touch the axis that it's rotating around, right? So it's going to be a solid figure. When we rotate it, it's not going to have any holes in the middle of it. Eventually, we're going to learn how to do one where it's got holes in the middle of it. But today, everything should touch the axis that you're rotating around. So your assignment, and we got a little while to work on it, so hopefully you can get started and get a little ways here. It's going to be from page 425, 1379, 13A, 14B, 25, and 33.